Hello. Today I will present you our work titled as Elevation Stat Space, which is a Surfel-Based method for navigation in 3D environments for mobile robots. So there is an increasing demand for robots in more realistic uneven terrains. And such environments are construction, rural disaster, planetary discovery sites. Currently, there is 4 major methods that robots navigating in such environments use. So we have 2D occupancy grids, full 3D maps, elevation maps, and also meshes. That's usually based on 3D point clouds. So we propose another alternative to all of these methods, and the reason for this is we have some limitations for each of these representations. So, for example, in digital elevation maps, we're not able to model some structures that overlaps. And in 3D occupancy grids, there is a curse of dimensionality, and we also have one issue that each of these different environment representation needs to be adapted to different motion planners. So we see this as an issue. And we propose work that deals with these issues, or work enables a seamless integration between motion planning and environment representation. It's also operating in full 3D, yet it does not suffer from the curse of dimensionality because we use point cloud maps, and we are only interested into the surface, to be precise, traversable surfaces of point clouds. So we have contributions as listed here, and example of the result from our approach. So there's an uneven gazebo world, and we want robot from here to get into the goal. So with our approach, we can achieve a near optimal path that goes under PR, depicted in here. Now, a little about approach. So first, we have a point cloud of the map, and we need to somehow discretize these environments. So we perform a uniform sampling for that, and we can select a radius for uniform sampling, so that this will determine the resolution of the area we're discretizing. And in each local neighborhood of these sample points, we can extract geometric terrain features such as roughness, tilt, and maximum heights of these neighboring points. So we can use these geometric features to regress costs to the point cloud map. And we have 4 critics. As I mentioned, there is tilt of the slope, there is roughness and maximum height difference in the neighboring points, and also ground clearance of the robots. So these 4 critics determine the traversability costs of that specific region. And these features are again all used using these neighboring points of the surface. So all of these equations are coming from the processing of the point clouds in each of the neighboring points here. And this finally results in a weighted equation here. So you can give more importance to a specific cost critic. For example, if you select omega t, then the point cloud map will be more sensitive to the tilts. And our elevation state space consists of 2 different components. So here we have the projection of SC2, and this can deal with kinematic constraints of an Ackermann type robot using Dubin's or redshift stat spaces. And additionally, we have a Z, which is elevation itself. So this is coming from the surfels that we are using on the surfaces of point clouds. And we implement this elevation stat space into OMPL, and we construct a new stat space. Since we have these surfels, and these surfels include the traversability cost of the environment, then we can use these surfels to generate valid samples only for sampling-based motion planners. Also, we can use terrain costs to get an objective that tries to minimize motion plans with respect to traversability costs. So in the experiment results, we have a scenario where our method successfully navigates an uneven terrain here, as shown in the sequences. So the robot starts here and progresses here and finally gets close to the goal. And whereas in classical ROS navigation, the robot creates a plan such as here. And once it gets close, because there is a hill here, so it starts to perceive this hill as an obstacle, but in fact it is not. So the robot changes its course according to new plan. And but even with that, the robot gets close to here, and again the traversable areas appear to robot as obstacles. So eventually the robot confuses and navigation fails. There is a sequence of experiments where we use Torvald robot to bring robot from this hill to down. So the robot starts here and then processes, follows the planet path, and finally it gets to the easier part of the navigation. So we have a video that shows the case here, and robot starts here and it's coming down of the hill as depicted in the upper left. And this is the view from the robot. So the robot keeps following the planet path and successfully reaches to the goal. We realize that once we use the valid Surfel-Based set sampler, the success rates of motion planners increase dramatically. PRM star here increases its solution rate by up to 5 times. And thanks to availability of surfels. Finally, we also had traversability based cost optimization. So here planners care about the traversability costs and try to go through the least traversability cost areas. And when we use OMPL planners, our method is able to generate plans that goes through safer areas. And this can be combined with other optimization objectives in OMPL, such as path length optimization objective. So in summary, we propose a constraint-aware stat space using surface representation of underlying point clouds. Our method is able to navigate robot in difficult uneven terrains. We performed experiments in both simulation and real world. And in contrast to previous works, our work enables a seamless integration between environment representation and motion planning. So this makes constraint planning for uneven terrains really effortless. And in future, we would like to look at the efficiency difficulties. When there is kinematic constraints for robots, the method suffers in terms of efficiency.